and I guess you will then upload the recording to Moodle.
Sure, to YouTube and then to Moodle. Yes,
so
yes. So what do I do now? Resume share. Yeah, screen sharing. This is what it is. Screen sharing and then recording. Yes. 8 participants plus 3, this is 11. Missing 5. Oh, 9, okay. Oh, it's up to you guys. Just don't switch on the lights over here. It's up to you guys. Up to you. But one person is not a student. This is Chris. We actually have only 8 people. But this is 11. Fine.
Good morning.
Okay, it's time to start. Good morning, everybody, and welcome to the lecture course on graph algebras, operator algebras, everyone can see. I hope everybody can hear me. I can see that I'm talking, so my computer tells me to talk to the Hajac, so I'm talking, but I hope you can hear me. And as much as we test,
it's very hard to hear you, at least for me.
Perfect, and I can also hear you. So even though we don't see you, we hear you perfectly well. So please do not hesitate to ask a question during my presentation. All right, so I decided to start with an overview, and I beg you not to get scared with this because there's plenty of material which I am showing you just to motivate why I'm fascinated with graph algebras. But I will not do everything I'm going to talk about today. So this is like a panoramic perspective. I want to also show you some key motivation for graph algebras coming from K-theory, but please don't be alarmed. Okay, but especially like 7 of your PhD students, I think it would be silly of me just to do like a regular algebra. I want to show you the research work. Okay, uploaded stuff to the Moodle. So in particular, the first exercise, list of exercises already Moodle site. And now let's rock it. Okay. So first, when it comes to the plan of the course, we will begin by doing graphs, combinatorics of graphs. So it's completely accessible to everybody. In fact, the first proper lecture will be given by my daughter. She gave this lecture in Boulder, Colorado, when she was 15, and we recorded it. And I'm going to play it next week, just to prove the point that this is actually accessible to children. And because I know hard concepts, the two combinatorics of graphs, I don't know how much time we spend there.
Excuse me?
Yes.
It's a bit hard to hear you.
Okay. I can. But I'm not going to walk around anyway. So, this device on my. Now I have mic next to me. Can you hear me better?
Yeah, now it's perfectly clear.
Okay, good. Now I have everything. I have a mask, I have headphones, I have a microphone. And I have gloves, so I feel like, being in some spacesuit. Okay, so first we'll devote some time into finite paths, actually much more than we need for the rest of the course. But when I was teaching it in Colorado a year ago, we discovered certain funny theorem, which we didn't expect to prove. When I spoke to some experts who do graphs for breakfast, they told me that, well, the theorem is correct, but it's probably new. It's funny because everybody can prove it. I mean, it requires absolutely no knowledge. It's pure combinatorics. And experts doing graphs, I don't know, computer scientists, engineers, whatever, they say they didn't see it before. So I'm going to devote some time into finite paths and counting finite paths, but this is just for fun. This is just to show you that you can have some fun without, it's like playing chess. You don't need any special knowledge. And who knows, maybe it's important for some engineers to have such a result. But then we'll do some more serious stuff. We'll talk about hereditary and saturated subsets. This is ABC of graphs, and you need these concepts in order to do graph algebras. Then there will be a more subtle concept of breaking vertices. So breaking vertices appear when you have infinite emitters. I have never seen actually people assuming it when it comes to the graph that the set of arrows and the set of vertices are countable. But I've never seen any example with, I don't know, somebody having a continuum of edges emitted from one point. I don't see why we cannot have it. But I will always think about, of course, we'll have plenty of infinities, otherwise it would be boring. But we will have these infinities countable, okay? And whenever you have infinite emitters or have one vertex which emits infinitely many arrows, then you have to be a little bit more subtle, and you have to discuss what you mean by breaking vertices, unbroken subsets, subgraphs in graphs, and so on and so forth. And then you can cook up a concept of admissible graphs, subgraphs. That's what how we baptized it. And people sometimes call them quotient graphs, but I think this is just completely wrong, because what are quotients are graph algebras. They are quotients, but we are really talking about subgraphs. So we decided to go against the terminology in the literature. And then finally, the sort of the highlight of everything, once we go into really into path algebras, Levitt path algebras, and graph-Pfister algebras, well, we will try to define morphisms between graphs in such a way that it will be a desirable category. Because you see, you can very easily turn graphs into a category by having an obvious concept of morphism. This is totally trivial. And it's useful. It's been used very heavily in mathematics in some breakthrough papers in Invenciones for studying three groups. So this usual concept of a category of graphs is useful, but not for us. Not for us when we try to do graph-Pfister algebras. And this is, if you want, work in progress. So we have some first results, but we are still far away from satisfactory position. And this is sort of, we'll touch on the frontier of research at this point. And then, well, the second part will be doing algebras with graphs. So first you have an obvious concept of path
algebras. It's obvious because basically you do it in such a way that you have a graph. When you have a graph, you construct finite paths, and then you take the linear span of finite paths and you multiply by concatenation. So whenever two paths meet, and you join them as a result of multiplication. If the end of one path misses the beginning of another path, multiplication is zero. So you have a very, very important and very obvious concept of path algebras. This is sort of, if you want, like a generalization of a tensor algebra, something very universal and very useful in classification, for instance, of finite algebras, not C-star algebras, that's trivial. Finite algebras without assuming them to be C-star. This is how it's done, and is also very important for representation theory. But then we will steer clear from this direction. This is a different course if you want. And we go into Leavitt path algebras, and then graph C-star algebras. And for instance, well, Jacek will understand it, because if you know compact quantum groups, then inside every compact quantum group, you have a Hopf algebra. You have this algebraic backbone. So if you want, Leavitt path algebras are to graph C-star algebras what Voronowicz-Hopf algebra is to a compact quantum group C-star algebra. Okay, this is this algebraic backbone that is inside, and you can see that if you take the universal enveloping C-star algebra, the Leavitt path algebra, then you get exactly graph C-star algebra. But surprisingly enough, this is not how the subject was developed. The history is quite different. And now the literature. So, well, the most basic reference is my paper with Mariusz Tobolski. We want to turn it into a book during this semester. So what I'm going to do, I'm going to rewrite this file. Yeah, on the go, when preparing a new lecture, I will just rewrite this paper, and we'll post a new version of Moodle. And I hope that at the end of the day, it will turn into something publishable as a book. Now, when it comes to existing books already, Leavitt path algebras is a very nice book, and it will be the most important book for our course. Yeah, so many things we're going to use are proven or studied or discussed in this book, Leavitt path algebras. Okay, so that's the main reference. Then I found that this book on algebra and representation theory by Karin Erdmann and Thorsten Holm is somehow very related to what we are talking about. You know, there are zillions of books on abstract algebra, but this book is somehow the closest to what we are doing. Yeah, so this is a very good reference. And finally, for these of you who are not familiar with C-star algebras, so this excludes Jacek, we have a very nice book of Gerard Murphy, C-star algebras and operator theory. This is my favorite book on C-star algebras, because on one hand side, it's not very long. I mean, it's not like Addison Ringrose, 3 volumes, 500 pages each. And on the other hand, it's not as concise as Invitation to C-star algebras by, what's his name? William Arveson, right? So it's somehow, and it's, I find it very appropriate for non-commutative topology. It has all basics over there. It's sufficiently clear to be able to just read it on your own. And on the other hand, it doesn't have zillions of pages. Okay, next, prerequisites and outcome. First, prerequisites. Well, as I was promising to you, the course is basically self-contained. The only thing I refuse to teach you is linear algebra. I assume that you know linear algebra, and this will not be taught. I also assume that you know basic functional analysis, like Hilbert space, Banach space, completion in norms, and all that stuff. But taking into account that 7 of you are PhD students, I take it for granted. Okay, but we will cover some more, well, I don't know to say advanced because it's still elementary, but we will cover some things in algebra like exact sequences, modules, protective modules, ideals, unitization, minimal unitization of algebras, all that basic algebraic stuff, which we'll need for the course. So this will be covered, but this will be covered during this recitation classes, Ćwiczenia. This is when we will do this, okay? And my plan is to ask PhD students to teach on some particular topics which are the closest to their hearts. So some people are more friendly with functional analysis, then they can do C-star algebras. Some people can do exact sequences and so on and so forth. So this will be this kind of development during the recitation classes. Okay. And now, well, as I said, we will touch on the state of the art. So anytime you feel like hopping in and doing some research, you're more than welcome, and you can do it at any level that suits you. So this is another thing which I find exciting about this subject, that this it is such a low entry to doing research, and yet research is not niche, it's not very easy, and there are many people who are interested in it from many different aspects. For instance, we have one collaborator in Boulder, Colorado, who is interested in graph algebras from the point of view of quantum computing. So it has many interesting links. Now, one of the things which I promise not to teach during this course, but this is like a key motivation for doing graph sister algebra, is K-theory. Okay, K-theory is like mainstream mathematics, both in classical geometry. If you think about big names like Atiyah, Hirzebruch, this is exactly where you have it, K-theory. And then also for sister algebras, the famous Elliott's classification program of sister algebras basically first and foremost uses very sophisticated K-theory. And on the side of geometry, this is the study of vector bundles. You can say a lot about the space when you study some Grothendieck group of vector bundles, and you can say a lot about sister algebra when you study Grothendieck group of finite geometric modules. So this is a key motivation. And if you want what graph sister algebras do for you, they offer to you a presentation which is particularly friendly for studying K-theory. Okay. So often the way one does research is that you have your most favorite sister algebra, or if you want to be without completion, you can also do Leavitt path algebra, and you want to compute its K-theory, but it's usually very difficult. So what you do, you prove, and this is where the difficult part comes in, by using some, representation theory. You're going to Hilbert space, you have one representation, another, then you say, aha, there's a unitary operator that intertwines them, so the sister algebras are isomorphic. These are non-algebraic isomorphisms typically, but you can turn your favorite sister algebras into graph sister algebras. And once you have this graph sister algebraic presentation, then you can just read off the K-theory from, for instance, Rebel-Szymański theorem. And there are also a lot of results concerning the generators, because in K-theory, one of the things which you want to do is not just to have the homological algebra and understand the K groups, but you also want to understand the generators, because this is where the fun is. This is where you have some concrete information about what you study. Okay. Now, but as I said, we begin by studying path algebras in a very elementary way. Then we go through all these definitions of hereditary saturated subsets, breaking vertices, and admissible subgraphs, and so on and so forth. And here there will be the first thing which is relatively new. We just published this result like, I don't know, 2 weeks ago. It appeared. It's my joint work with Mariusz Tobolski and Sarah Reznikov. It's a very small result, but we did it, and it's very intuitive. You see, when you want to glue spaces to obtain more fancy spaces, well, you can do it. This is the standard concept of a push-out. To get a two-sphere, you have two disks and you glue them over the boundary circle. This is how you get a sphere. And it turns out that you can do something like this with graphs. You can take two graphs and glue them together over subgraphs to have the union graph. And then you would like to see that somehow this translates into the sister algebra, and that you get a pullback of sister algebras. And that's what we can prove. This is what we can prove. Here, the key thing is that if you have the intersection graph being admissible in each of the two graphs, and if you have each of the two graphs unbroken inside the union graph, then they're also admissible then these two graphs are admissible in the union graph, and then the morphisms exist, and you have a pullback diagram of sister algebras, and this is what you want when you study graph sister algebras. So we somehow took the issue of breaking a complicated graph sister algebra into a pullback of simpler graph sister algebras. So for instance, you can use the Meyer-Vietoris technology to compute K-theory and stuff like this. And we took it down from the level of function analysis of algebra into the level of pure graphs, which is much easier, because then this is something very tangible, something very hands-on, and gives you the intuition, which is normally provided to you in algebraic topology by spaces, but here it's provided to you by graphs. And then, as I told you, we want to somehow evolve from this standard morphism of graphs into what I baptized as the Leavitt morphisms of graphs, but it's not really defined yet. I mean, we are searching for the right concept. And you can help me with it if you wish. We have some ideas, so this is not an empty phrase, but this is far from satisfactory at this moment. Okay, now I already told you how we define path algebra. And then once you have a path algebra, and people who classify finite dimensional algebras, people who study representation theory, they have their theory themselves. They study particular ideals in path algebras, and this is how they can do the representation theory and classification. But we do something else. We take Kunst-Krieger relations. They are very specific relations that come from function analysis. In fact, these two guys were, I have completely no idea what it is, but these guys were studying some Markov chains, stuff like this. I completely don't understand it, but it didn't come from algebra. Yeah, and then they came up with a concept of graph sister algebras, completely somehow, if not unaware, then at least not using path algebras. and they defined these sister algebras, and they turned out to be very, very amenable to K-theory. So quickly people fell in love with them, and the whole field of mathematics was created. But at a certain moment, I think in 2004, people somehow realized that, wait a minute, inside these graph sister algebras, there are very interesting dense subalgebras, Leavitt path algebras, and you can define them in a very systematic way, coming from path algebras, as it should be done. Yeah. So this was tidied up in 2004, which is amazing because it's like, what, 20 years after the inception of graph sister algebra theory. And now we have this big boom of people studying simultaneously Leavitt path algebras and graph sister algebras. But it's kind of funny that analysis was first, and really like by 2 decades, I think, and then algebra came. But this algebra tidied up a lot of things, and in particular, it's far more systematic, far more comprehensible. When you start from path algebras, then you go to Leavitt path algebras, and then you take the universal enveloping sister algebra. And the way you do it here, you have to, because you see, once we do sister algebras, we have this concept of an involution. So what we do is that we take a graph, and then it has vertices and it has its edges. But in order to somehow go through path algebras, you have to add ghost edges. So keep vertices as they are, you don't change them, but you double the set of arrows. So for every arrow that you have, you also add an arrow going in the opposite direction. Okay, just reverse the arrows. They are called the ghost arrows. And then you have so-called extended graph. And then you take the Leavitt path algebra of the extended graph, and then you divide by Kunst-Krieger relations, and here you go. You have Leavitt path algebras. You take the universal sister algebra of this star algebra, and you get graph sister algebra. And the involution is obvious. You send an arrow to its ghost, and it sends the ghost arrow to the arrow of which it is the ghost. Yeah, so this is the involution, and if you want, vertices are self-adjoint. Okay, and then I want to somehow show you how it is applied in non-commutative topology. I will explain what I mean by non-commutative topology in a second. But I already somehow mentioned it. The goal is the following: we want to create the category of graphs in such a way that when we study push-outs in this category of graphs, and then we apply the functor assigning to a graph its Leavitt path algebra or its graph sister algebra, then it becomes a contravariant functor, turning push-outs into pullbacks. This is what Gelfand functor does with compact Hausdorff spaces and going to unital sister algebras. Okay, so we somehow want to achieve this goal. And we have plenty of examples. You see, what I like about it is that it wasn't one of these why not studies, why not generalize, why not do this, why? No, I mean, we have plenty of examples which we try to understand. And when we try to understand them of why we really work, certain theory emerged, but it's far from complete. And maybe some of you will help me complete it. Okay, now this was the introduction. I think this is enough of soft talk. Now we can show some theorems and do some mathematics. again, that part will not be, so what I'm going to tell you about right now is non-commutative topology. We're going to do examples on non-commutative topology in the course, but not the theory of non-commutative topology. But I want you to understand the background and the motivation. So first you have this concept of a sister algebra. And one of the way you can think about it is that it is a complex algebra of continuous, which means bounded linear operator on a compact Hilbert space, complex Hilbert space, satisfying just two conditions. It's topologically closed in the norm topology of operators, and is closed under the operation of taking adjoints of operators. So this is a theorem that says that every sister algebra, which can be defined abstractly as a Banach algebra with some involution satisfying some properties, is actually an operator algebra. So in other words, you always have a faithful representation on a Hilbert space of your sister algebra. So it's always an operator algebra. So you can take it as a definition if you wish. Now, the reason why we somehow view sister algebras as tools of non-commutative topology is because of this very famous Gelfand-Naimark theorem, which says that every commutative sister algebra is naturally isomorphic to the algebra of all continuous complex valued vanishing and infinity functions on a locally compact Hausdorff space. So if you just take a locally compact Hausdorff space and you take all complex vanishing and infinity continuous functions and you take them with pointwise addition and multiplication, then you obviously get a commutative algebra. It's also obviously the sister algebra where subnorm with a norm given by the supremum, right, of absolute value of a function. So obviously, every space, every compact Hausdorff space, every locally compact Hausdorff space will give you a commutative sister algebra. This is completely clear because point-one multiplication of functions is commutative. But what is absolutely remarkable, and this is a very difficult and beautiful theorem, is that whenever you have a commutative sister algebra, you have no choice. You always can construct a space, a locally compact Hausdorff space, such that this is naturally isomorphic to the function algebra. Okay, so this is, if you want, the cornerstone of non-commutative topology. And now, if you want to put it in a more elegant way, not the way Gelfand and Naimark did it in 1943. I'm always amazed how people in the middle of the Second World War do such beautiful theorems. I mean, it was 1943, it was hell, and they proved such a theorem. Let's try to do it elegantly using the language of categories. So if you denote by CH the category of compact Hausdorff spaces, and by CC star the category of unital commutative sister algebras, then if you look at the functor which assigns to a compact Hausdorff space the commutative sister algebra of all continuous complex valued functions, that this contravariant functor gives you an anti-equivalence of categories. Okay, so this is what I mean by saying that this theorem is natural. So this assignment of spaces to commutative sister algebras and vice versa, function algebras to spaces is natural. Everything is functorial. This is very important. And this is expressed over here. Now you can wonder why I changed from locally compact to compact. Well, if you're an expert in this area, you know that there's a big deal switching between compact and non-compact. Many things change. Especially when you study groups. The theory of compact groups is much different from the theory of locally compact groups. But you see, when it just comes to this point, the trouble here is that when you are talking about locally compact Hausdorff space, it's not exactly obvious what your morphism should be. I mean, everything is done, clarified, but it's complicated. I would have to explain it for half an hour to get all the subtleties right. But when you are compact, a morphism is just a continuous map. And we take the pullback of a continuous map and it becomes a homomorphism of sister algebras. That's it. But the moment you are non-compact, well, then you have to think what proper maps and then what is a morphism, how do we must preserve approximate unit and so on and so forth. We have plenty of stuff to discuss. It's done, it can be done, but I wouldn't be able to explain it so quickly. And most of the examples we are going to study, if not all, are going to be compact Hausdorff spaces and unital sister algebras. So we'll be at this level. But it's important to know that it's more general. And in fact, if you just bear in mind that locally compact Hausdorff space is just a compact Hausdorff space with one point removed, then you see that there is not such a big deal in going from compact to non-compact for this theorem, but not for other aspects. Okay, and now a little bit of, if you want, ideology, interpretation. This is very much like with algebraic geometry. At a certain moment, using this what Stellensatz, Grothendieck decided, well, why should we study spaces? We can study instead the rings that we have of polynomials on these spaces. And the theory was developed more and more and more. But for Grothendieck, everything was always commutative. So in algebraic geometry of Grothendieck and others, of course, you have all your rings, all your algebras are commutative. But then you have, this is a very fundamental, beautiful discipline of mathematics. And you go way beyond just algebras. You have to take some ring spaces, so you assign some rings to some subsets and so on and so forth. So this is a very beautiful and very complicated theory. But if you want what Grothendieck and others kept in algebraic geometry, they kept commutativity and allowed for everything else. Okay, if your ring is very, very good, then it basically describes a space. But then you can give up on these good properties, and then you can take, instead of one ring, you can take some, I don't know, sheaf of rings and stuff like this. And this is how you get algebraic geometry. In non-commutative geometry, non-commutative topology, what you do, you always keep one algebra. It's always a sister algebra, one algebra. But then you drop commutativity. Okay. So this is, in this sense, this is complementary. Non-commutative geometry is complementary to algebraic geometry, but the idea is the same. This is this Copernican-style revolution when we don't think about algebras as objects revolving around the concept of a space. No, we think that the primary concept is the concept of an algebra or something based on an algebra, and when we define points as characters. So the concept of a point, the concept of a space is revolving around the concept of an algebra. That's why I call it Copernican-style revolution. And because precisely of this Gelfand-Emmerich theorem, that you know that every unital commutative sister algebra is just the function algebra on a compact Hausdorff space, and moreover, this correspondence is functorial, so you also have the dynamics inside. Morphisms are preserved. Instead of having continuous maps, you have star homomorphisms. This is why when we look at unital non-commutative sister algebras, we think about them as compact quantum spaces. Okay, and this is the starting point of non-commutative topology and what we are trying to do, and then subsequently non-commutative geometry. Right, when you study differential geometry, first all your manifolds, all your spaces are topological spaces, but then you have further differentiable structure over there. The same is in here. Have non-commutative topology based on sister algebras. For K-theory, that's all you do. But then you can be more subtle. You can introduce spectral triples, Dirac operators. So this is corresponding to putting this manifold structure on topological spaces. And that's a very hot topic, non-commutative geometry. But we are going to focus on non-commutative topology in this course. So we will not go into differentiable structures. We'll just do sister algebras. And using sister algebras, we'll study topology. Yeah, and we can do it because of this equivalence. However, this is why actually it's so interesting, because this reformulation is everything but easy. In fact, it's almost always difficult. So for instance, you want to define a compact quantum group, okay? So it seems that, well, it's completely obvious. You take Hausdorff space, and now you have to put group multiplication. So it's a certain morphism. Cartesian products go to tensor products, and then you pull back it. Then you put some axioms. Well, as far as compact Hausdorff semigroups are concerned, that's fine. But then if you want to define the inverse operation, if you want to make sure that for every G in G, you have G inverse, but you have a continuous map which assigns the inverse to each element, so it's a group of the semigroup, all of a sudden it turns out that it's very difficult to do it when you drop commutativity assumption. And in fact, there is a beautiful theorem that says that if you have a compact Hausdorff semigroup, with cancellation properties left and right, but it must be a compact algebra group. But this is a beautiful theorem. When I was lecturing at the Department of Physics, it took me 90 minutes to keep a complete. It's a standard theorem, but it's a theorem. And then you can use this theorem, this unusual presentation. Instead of defining a map, you have to speak some cancellation properties. But it turns out that this fancy theorem is exactly what is translatable into non-commutative sister algebra. And this is how Voronovich defined compact quantum groups. That's why the very definition of a compact quantum group was a big achievement of Voronovich. It wasn't just, okay, let's mimic everything, write everything in terms of sister algebras because we can, because we have its anti-equivalence of categories, and then drop commutativity. In 99% of the cases, when you do it, it will not work. I mean, you will get some conditions, but they will not make any sense when you drop non-commutativity. Okay? So the name of the game is to reformulate your classical topology in such a way that it's equivalent to what you know from textbooks, but then it's done in such a way that it still makes sense when you express it in terms of sister algebras and star homomorphism and drop it. Okay? So I just gave you an example with compact quantum groups. I think one of the few exceptions is that it's straightforward is with K-theory. Okay, and as I promised to you, we're going to glue graphs together. And this is like the main motive of the course. This is what we are going to cover. And we want to do it in such a way that once we study commutative sister algebras, well, we know that they are just function algebras on spaces. And when we do pullback diagrams of commutative sister algebras, they correspond naturally to push-out diagrams of spaces. So the name of the game is to go into graph sister algebras and see if we can represent pullback diagrams of graph sister algebras via push-out diagrams of their graphs. Okay? This is the motivation. Now I'm doing it for spaces. Of course, push-out is a categorical notion. You can define it by some universal property, but let me be here just completely straightforward. And when I have the push-out in the category of spaces, or if you want topological spaces, if I'm in spaces, I have maps. If I'm topological spaces, I have continuous maps. And what is the push-out of x and y over z? Well, you have a map f from z to x, you have a map g from z to y, and the push-out over these two morphisms, if you want, is the following space. So first you take the disjoint union of x and y, and then you divide it by the equivalence relation here denoted by R, and it is defined as the smallest equivalence relation satisfying this property that every point coming from z via f is identified with the same point coming with a point coming from z via g. So this is if you want the gluing recipe. Okay, I have x and y which are disjoint. Okay, but if I have some point in x which comes from z, and I have some point in y which comes from the same z, one comes via f, one comes via g, then I identify it by my relation. And then I take the smallest equivalence relation, which satisfies it. That's the push out in concrete terms. Of course, you can phrase it using universal properties. Now, in particular, the most obvious push out that you have is when you take z to be just the intersection of x and y, and then take f and g to be subset inclusion. Okay? And this push out is obviously just the usual union, right? Because what I'm doing here, I take the disjoint union, and I say, aha, I take the disjoint union by identifying the points which come from the inclusion of the intersection. So that's exactly the definition, if you want, of the set theoretical union of two spaces. Okay, and let me give you some examples of why this is interesting. And in particular, it's interesting not only when you just take the union of spaces, but when you have some shrinking. So first thing, this is a push-out diagram. I shrink a circle to a point here. If this arrow is shrinking the circle to a point, it's a nice continuous map. And here, this is the inclusion map. I include S1 as the boundary of the union disk. Okay, two nice continuous maps. So what's the push-out? Well, it's a two-sphere. Why? Because what I'm doing here, by this push-out recipe, I'm saying, aha, I take the boundary circle of my disk, and I must identify, because of a definition of a push-out, I must identify all points on this boundary circle of a disk with one point. So I'm shrinking the boundary circle of a disk to a point. So I get this here. Okay. Is this clear? Okay. Next. The same works with
Yes.
real projective space. Well, I like to, well, the definition of a real projective space is that you take the two sphere, take the antipodal action of Z2 on the two sphere, and then you divide it by this action. So if you want to take the sphere and you identify all antipodal points. So one way of thinking about it is, well, you can take the disk and then you identify antipodal points on the boundary circle of this disk. That's yet another way to think about it. My favorite way to think about it is, however, slightly different. You take three squares, and then you put two squares together, but in such a way that you assemble them into a Mobius strip. And then the Mobius strip has the boundary circle, and then the third square you attach via its boundary to the boundary circle. So this is, if you want, splitting RP2 into three tractable spaces. And I like it because this Z2 principal bundle of S2 over RP2 trivializes over such color. But here you can think about it. Look, it's just exactly the same recipe, and S1 is exactly this S1, which, if you want, is the boundary circle of a disk, and then it has antipodal points identified. So you have the same recipe. If you shrink this circle in RP2 to a point, you'll get again into sphere. Okay, now. Well, it has a fancy name. It's called a weighted projective space with indices 1 and 2. But I like to call it kissing spheres. So here what I'm doing is the following. I put S1 into S2 as the equator. And I shrink this equator to a point. So what will I get? I'll get two spheres attached to themselves at just one point. Okay. But it has a name. It's called weighted projective spaces because you can obtain by as quotients by appropriate actions of the circle on a sphere. Okay. If you do the usual diagonal action, you'll just get the usual sphere, CP1, complex projective space of dimension 1. But if you tune your action differently, you'll have one phase acting differently on one component, and, different on another component with appropriate ratio, then you'll get a different quotient space. And, voila, here you go. Weighted projective space. But from the point of view of push out, well, this is how you can get it. You can just shrink the equator in the sphere to a point and get these weighted projective sphere, kissing spheres. And so that you don't think that I can only shrink to a point, let me be a little bit higher dimensional. Let me take complex projective spaces. Is everybody happy with the concept of a complex projective space? No complaints. Okay, but okay. There are many definitions. The one I like best is I take 2n plus 1 dimensional sphere. So it's given by the equation the absolute value of zi squared summed up over all i's is equal to 1, the sphere equation. And then you have these complex variable that satisfy one real equation. This is how you get 2n plus 1 dimensional real space. But then you can, of course, preserve this equation by rephasing each of your variables by the same phase, right? E to I5, the circle. Yeah, that's the diagonal action, because you act with exactly the same E to I5 on each and every of your complex variables. And this gives you a nice action of a circle on a 2n plus 1 dimensional real sphere. And when you take the quotient space, if you want, it's by definition complex projective space. So in particular, when you are talking three sphere, okay, so just z1 squared plus z2 squared absolute value is equal to 1. And then you act on z1 with e to I5, you act on z2 with e to I5, and when you take the quotient, you'll get exactly the two sphere. So CP1 is a two sphere, okay? But if you are more into algebraic topology and CW complexes, then if you look at this push-out diagram, then this is precisely telling you how to understand complex projective spaces as CW complexes. So, well, what I'm basically doing, I take a lower dimensional projective space, CPn minus 1, and I attach over the 2n minus 1 dimensional sphere, I attach a 2n dimensional ball. So I attach a higher dimensional cell. And when I attach it, I grow higher dimensional vector space. Okay. So this diagram reflects CW complex structure for vector spaces. And if you don't want to use fancy names, you can just say the following. So here, this arrow going from S2n minus 1 to CPn minus 1. This is this quotient defining CPn minus 1. So you have this diagonal circle action of your sphere. You divide by the circle action. This is the canonical quotient map, and this is your CPn minus 1. Of course, the sphere is the boundary of a 2n dimensional ball. This is 2n dimensional ball. And this map from the ball to CPn is a bit harder to define. But if you want, basically what you do, you extend this canonical quotient map to the inside of your sphere. Remember, this is the boundary sphere of 2n ball. You can do it. You can write the formula. You can land on CPn. This is the natural inclusion of CPn minus 1 in CPn. And this is a push-out diagram. Okay. So well, how can we say it? We can say that if I take the 2n dimensional ball and I shrink its boundary to CPn minus 1, I get CPn. Yeah. And if you are very low dimensional, you see, take n equal 1. CP1 is a two-sphere. CP0 is a point, right? And when n equal 1, you have 2 times 1 minus 1 versus 1. That's a circle. And 2 ball is a disk. So if you are very low dimensional, you see this very simple picture of shrinking the boundary circle to a point. But this works for all dimensions. Okay. So these are examples of push-outs. This is a motivation. And well, you can guess that I chose these examples for a purpose. Namely, we have non-commuted deformations of these examples. And the same story works, except that now, instead of spaces, we'll have graphs representing graph sister algebras that you obtain by deforming the spaces. Okay, so that's the name of the game. But now I have to tell you what pullbacks are. This will be part of this algebra intro we'll do in recitation classes. So again, pullback is a very categorical concept. You can define it in very broad generality by a universal property. But say if I am dealing with abelian groups and every algebra, sister algebra module is an abelian group, you can always add. There's always an additive structure. Yeah. Then in the category of abelian groups, you can define the pullback in a very concrete way. So now what I've got, I have an abelian group A, I have an abelian group B, and I have a group homomorphism into an abelian group C. So what is the pullback of P and Q? Because this is what you need. P and Q has both A and C and B and C. So actually take the pullback of P and Q, because once you have these two group homomorphisms, it makes sense to ask what's the pullback of this pair of group homomorphisms with the same target. Well, you say that, I take first the direct sum of these two abelian groups. I take all pairs with A in the first group and B in the second group. But then I restrict this space into only such pairs which are compatible via homomorphism. So I take only such pairs N and B with the property that P of A is equal to Q of B. And that's the pullback of abelian groups. But it works for modules, abelian modules, algebras, rings, okay, everything that has additive structures. And when you just make sure that your morphisms are in the right category, which is built on the category of abelian groups, it will give you whatever object you have in the category. So if this will be, I don't know, a homomorphism of vector spaces, this will be a pullback vector space. If it will be homomorphism of rings, it will be a pullback ring. If it will be a homomorphism of algebras, this will be an algebra. If this will be sister algebras and this will be star homomorphism, this will be again a star algebra, because this is a continuous condition. Okay. Now, this is a very important point, and we will do it at a certain moment in recitation classes. I hope the full proof. Namely, it shows you that when you take this Gelfand functor, assigning to a compact Hausdorff space. So now let's be specific. Let's not mess around. So here this was completely general, right? Now I want to take X and Y. So if you go back to the previous slide, All these guys are compact Hausdorff spaces. So here I could be very vague. I could speak sets and maps. I could speak topological spaces and continuous maps. But imagine that we are doing the push-out diagrams in the category of compact Hausdorff spaces, and all maps are continuous. Okay, so that's the category we're interested in, and these are examples in this category. And so now my X and Y are compact Hausdorff spaces, and F and G are continuous maps, F from Z to X and G from Z to Y. Okay, and now you can prove the following thing, that the Gelfand functor, which turns a compact Hausdorff space into a commutative unital sister algebra of all continuous complex valued functions, and which by pullback turns a continuous map into a star homomorphism, then this actually turns every push out into a pullback. Okay, so I take these two commutative unital sister algebras. When I take the pullback of a continuous map, I have a star homomorphism. Then here's the definition of a pullback. So what I do, I take all pairs of functions which are compatible, which agree over Z. And then you can prove that this pullback sister algebra is exactly the sister algebra of continuous complex valued functions on the push out of these two spaces. And now I want to give you an example which I hope will convince you that it is really very elementary. Imagine that this push out is really the union of sets. Okay, this is a special case. Let's think about the union of sets. So imagine I want to define the algebra of continuous functions on the union of two sets, X and Y. So what is a continuous function on the union of X and Y? Well, it's a continuous function on X and a continuous function on Y, and they must agree on the intersection. And this is exactly what we are doing. I take A to be my continuous functions on X. I take B to be my continuous function on Y. And when I say, haha, they must agree on the intersection. And this is how I have all continuous functions on the union. So that's the basic idea. Okay? It doesn't have to be just the union. It works for turning push-outs into pullbacks. And this is, if you want, our research goal for graph sister algebras. So this is what happens for unital commutative sister algebras. And this is well known. This is ABC of sister algebras. And somehow we want to mimic this for graph sister algebras. We have some first results. In particular, we are done in the case when this, I have to remember not to point on the screen, I have to point here. So that everybody can see, not just the three of you. We want to have it in this. So in graph sister algebra, completely done in the case when we take the union of graphs, then such a theorem is proven. Okay, but what we want to do, because we have lots and lots of interesting natural examples, we want to do it for more general things like push-outs, and we have first result, but under many assumptions, and we would like to somehow see how far this can go. Okay, so this is the part which we are going to cover. So push-outs to pullbacks. This is what I want to do during this course. Now, again, something which I'm not going to cover, but I want you to bear it in mind as kind of a motivation. At the beginning, when I was talking about motivations for doing graph sister algebras, I mentioned K-theory, vector bundles, and so on and so forth. I realize that at least for some of you, these words do not mean anything. So let me just give you some very, very fast crash course on what K-theory is about. Well, K-theory is for spaces, for differential geometry, is for studying vector bundles over manifolds or marginal topological spaces. Okay, and well, you can have the trivial vector bundle, which is what? You take some space, say a circle, and you multiply it by a vector space, Cartesian product. This is the trivial vector bundle. Okay, but you can be somehow more subtle. If you are very sleepy in the morning and you try to put your belt together, then sometimes you do a Möbius strip. The angle is wrong, and your belt becomes a Möbius strip. And you see here, this is no longer true. This is no longer true that this construction is just a Cartesian product of a circle and a space. It is not. It locally is, right? if I chop this circle into, I don't know, some pieces, then over some pieces, yes, it will be exactly an arc times a vector space. But I have some non-trivial gluing in between. So this is the idea of a vector bundle. And it turns out that the study of vector bundles over a space tells you a lot about the space. And yeah, this is how you have Atiyah-Hirzebruch K theory. But one of the things which you can prove is sort of following the spirit of Gelfand-Naimark theorem. Well, first you notice that if you take any complex vector bundle over a compact Hausdorff space, and then you take the module of all continuous global sections of this vector bundle, then you can realize that this is in fact a finitely generated projective module over the sister algebra of continuous complex valued functions in space. Right? You can prove it. And like with the Gelfand-Naimark theorem, the reverse is also true. So moreover, that you take any finite generated projective module over such a unital commutative sister algebra, then it will be naturally isomorphic to the module of continuous global sections of some vector bundle. Okay. So if you want, we are boosting the Gelfand-Naimark theorem from just spaces to vector bundles. And if you want to see how you recover the original Gelfand-Naimark theorem, well, this theorem is relatively easy because you have already Gelfand-Naimark. Okay. And you can see Gelfand-Naimark as a particular case, because what is the algebra of functions in a space? Well, you take the trivial line bundle, so you just take your space cross complex numbers. So then continuous global sections of such a trivial vector bundle will be precisely functions on your space. Okay? And that's how it works. Now, this theorem goes under the name of Sir Swan, but it's kind of funny. It's not like these two guys work together and publish a paper. No. No, Sir did it in the category of algebras, and Swan did it in the category of sister algebras. So one is algebraic, one is functional analytic. But they fit so nicely together. This is basically the same theorem. So it goes under the name of Sir Swan. Okay. So what I'm telling you, just as I did with Gelfand-Naimark theorem, that it's not only that you have this correspondence that every finite projective module of a commutative integral sister algebra is in fact coming from a vector bundle, but I'm also telling you that this correspondence is functorial. So I can phrase it in the following way. If I take CVB to be the category of complex vector bundles over compact Hausdorff spaces, and FGP the category of finite generated projective modules over unital commutative sister algebras, then this assignment to a complex vector bundle, I assign the finite generated projective module of all continuous global sections, then this assignment gives you an anti-equivalence of categories. This is a contravariant functor which establishes anti-equivalence of categories. This anti is only because of contravariance. Okay. So this means these are basically the same things, okay, in a natural way. And this is why when we go to non-commutative sister algebras, we think about finite generated projective modules over non-commutative sister algebras as non-commutative vector bundles. And this way, we take the famous Atiyah-Hirzebruch topological K-theory of complex vector bundles, we take it into sister algebras. And this correspondence is relatively easy. This is one of these examples where dropping commutativity didn't change anything. It works just as well. And the value of K-theory in studying sister algebras, operator algebras themselves cannot be overestimated. If you look at famous Elliott's classification program, it's K-theory, and one more time K-theory. Of course, it's far more sophisticated than just plain K-theory, but at the root of everything is K-theory. Okay. This is kind of amazing that this kind of tool allows you to study sister algebras themselves. And if you want an example of why K-theory, I just want you to bear in mind, K-theory is the mainstream of mathematics. Why it was so important to begin with is the famous Milnor solution of a sphere problem. I mean, he did it using K-theory. There's a very famous problem in topology concerning vector fields on spheres. This is a very, very difficult problem, and Milnor solved it using K-theory. So it has tremendous application. This is a gigantic tool. And I dare say that the Bott periodicity, which you have for K-theory, which in fact implies the famous Atiyah-Singer index theorem, is one of the most important theorems in mathematics ever. It will be in some top 10 list probably. Okay, so this is very important, and this is what I mean by non-convex topology. So it's not just sister algebras and pullbacks, but also the study of K-theory. But this is not part of this course. This is just a motivation. Yeah, remember what I told you is that graph sister algebras are particularly friendly for studying K-theory. Okay? Okay, so I think this is the end of motivational part. So now we are really going to do definitions and examples in the remaining 48 minutes. Okay, so now please, if you fell asleep, please wake up right now, because everything from now on, I'm going to use it later on. Okay. First, we have finally, I was mumbling about graphs and didn't define it yet, but this is a very elementary concept. So I hope that you at least had some idea. But here it goes, a formal definition. So what is a graph? It has many names. It's called sometimes an oriented graph, sometimes it's called a quiver, and it's hopeless. In the literature, it's all confused. You have to be very careful, because when you just say a graph, it can mean different things. You just Google it up in Wikipedia, you can have many different things. In particular, people often study unoriented graphs. No, for us, graphs are oriented. So what is an oriented graph or a quiver? To be honest, I love the name quiver, Kochan, because it reflects exactly of what we are doing. So Dan Quillen used the concept quiver, but forget it. I mean, this is so deeply rooted now that people call them graphs that it's unchangeable, unfortunately. If they're up to me, I would call it quiver algebras and so on and so forth, but it's hopeless. You cannot change it now. Okay, so what is a quiver? What is an oriented graph? What is a graph? It's a quadruple. So you have two sets, E0 and E1, and you have two maps, S and T. The set E0 is the set of vertices, and the set E1 is the set of edges. I also like to call them arrows. Well, again, because these are oriented edges, so why not call them arrows? And S and T are the source and target maps. Sometimes instead of T, you have an R, and it's called a range map. It's completely interchangeable, target or range. And what they do, the source map assigns to each arrow its beginning, and the target map or the range map assigns to each arrow its end. So if you want these S and T, they define an orientation. Right? Take your edge, apply it to your map S and T, and then you know which vertex is at the beginning, which vertex is the end. So these two maps S and T give you an orientation of the graph. Okay. So this is a very simple definition to remember. And as I said, people often don't assume anything about how big these sets might be. Okay. But I've never seen anything which would go beyond countable infinity. Never. But on the other hand, I cannot tell you, oh, yeah, this wouldn't work if a set were uncountable. No. And the second part of the course is what a graph sister algebra is. Now, when I have a graph, I can tell you what a graph sister algebra is. Okay. And the whole course is based on these two definitions. Everything else is sort of filling up the space. Okay. But I want to go from this very elementary, childlike mathematics of graphs. I mean, childlike in the sense, conceptual sense. You have lots and lots of very difficult problems. It's not easy mathematics, but conceptually it's very easy to comprehend because this concept is very simple. And here you'll use it as a tool for understanding some very non-trivial aspects of function analysis, operator algebras, and its K-theory. Okay, so what is a graph sister algebra? So of course we will define sister algebras. We will say what it means to have universal sister algebra of a set of generators and relations. It all will be done. Yeah, but please bear with me. I at least want to give you the gist of what's going on. So once you have a graph, and now you know what a graph is, okay? You define its graph sister algebra in the following way. You take your vertices And to each of your vertices, you assign a projection. So an idempotent which is self-adjoint, okay? A projection. And to every edge, you assign a partial isometry, okay? And these are your generators. So your C-star algebra is generated by these projections and partial isometries, but it's subject to relations, the so-called Kunz-Krieger relations. First relation is the following. This somehow explains of what I mean by partial isometry. So first, and that's very much in the spirit, of path algebras, if you take your two edges, x and y, and x happens to be different from y, then the partial isometry star assigned to x multiplied by the partial isometry sy assigned to y must be 0 if x and y are different. But if x and y happen to be the same, this is exactly what I mean by partial isometry. Right? Isometry I have when s star s is equal to identity. This is isometry. This preserves the scalar product. Yeah? But it's partial isometry instead of being equal to identity is equal to a projection. This is why it's called partial isometry. And what projection is it? Well, this is exactly the projection that you assign to the end of your edge x. So you take an edge x, you assign to its partial isometry as x, and it's a partial isometry with respect to which projection? Well, exactly to the projection which is the end point of your edge, assigned to the end point of your edge. Okay, so this is the first relation, and if you want, this is edge related. I just study edges and tell you what happens. Okay. Now, the second relation concerns vertices. So I take a vertex and I assume it to be a regular vertex. So a vertex is called regular when it emits at least one and at most finitely many edges. Okay. It might happen that you have an edge which is so-called sink, it doesn't emit anything. Things at most come to it, but nothing goes out. This is a sink. Then you cannot sum over an empty set. And also, the sum is meaningless if it were infinite. So if I have a vertex which emits finitely many but non-zero edges, then this is a finite sum. Okay. And now look, I multiply these partial isometries, but in the other order. I multiply them in the other order. And now I'm saying that the sum is equal to the projection, which is at the beginning of all these edges. Okay. So the situation is reversed. So look, there is a certain very important asymmetry. When you multiply s star with an s, that's simple. You don't care what happens at the vertex, which gives you this partial isometry property. It's irrelevant what other edges emitted at this vertex, what edges come to this vertex is irrelevant. Okay, but here it is not. Here you start from a vertex, and you look at all edges emitted from this vertex, and only then you can write this condition. Okay, and then you have the third condition, which is only for the infinite case. I mean, I can write it for every case because it's always true. I say that Sx star is always less or equal than the projection assigned here. And in case you're wondering what do I mean by inequality for algebras, well, that's very simple. You say that a positive element, well, you can say that the element in your C-star algebra is positive if it has a positive real spectrum, non-negative real spectrum. Or you can say that your element in C-star algebra is positive if you can write it down as x star x, a star a, right? Then it's positive. And you say that two positive elements satisfy an inequality if their difference is a positive operator, a positive element in your C-star algebra. So this makes perfect sense in C-star algebras. Let's write it down. But I will show you how to do it purely algebraically. Okay. This will be one of the things which will come up in the course. You can completely dispose of this analysis, and you can write it down in a purely algebraic fashion. But this is important only for infinite emitters. Okay, so of course, if you have a vertex which doesn't emit anything, then there's no x. So we have an x; it must have a source. So you go to its beginning, and of course, this is already not a sink because it emits at least x. And if it emits infinitely many edges, then fine. I just take this one particular edge I take a positive element which is obtained by Sx times Sx star, and I say that it's less or equal than the projection assigned to the beginning of the section. Okay? And if it so happens that S of x is a finite emitter, you see that this condition number 2 implies the condition number 3. Okay? Because then my x here is an element of this sum, and all that I'm saying is that if I take the sum of positive elements, then one positive element is less or equal to the sum of positive elements. That's obvious. Okay. So condition number 2 implies condition number 3 in case S of x is a finite emitter. But if it's an infinite emitter, well, we want it. And maybe it looks, very unfriendly to pure algebraists, but I will show you that you can, using Leavitt path algebras, you can phrase it in a completely algebraic way. But this is traditionally how it's defined. And this is the definition I'm putting forward in front of you. And I want to go from this definition to that definition in a very systematic way. So this is sort of the gap we are filling in. You have lots of literature on Leavitt path algebras, on graph sister algebras, but they don't study graphs too much. It's already going into algebra, okay? Sister algebra or algebra, but it's already going into algebra. But in order to do it in a very systematic way, there's a lot of stuff to be filled in, exactly for like half of the semester course. And this is what we are doing. I'm not aware of any book, of any paper which would very systematically study graphs from the point of view of Leavitt path algebras or graph sister algebras. Okay. So this is what we are going to do. So I want to do it in a very systematic way. I want to go from graphs to path algebras, from path algebras to Leavitt path algebras, and from Leavitt path algebras to the universal enveloping sister algebras. Okay. This way we'll go from definition at the top to the definition at the bottom. Sure. Sure. Mm-hmm. No. Wait. Think about it of course, these are operator algebras. We have representation on a Hilbert space. We will get into it, not today, but during the course. But you should think about it as the universal algebra given by generators and relations. Typical way you define an algebra, you say, okay, what are polynomials in n variables? I take n variables x1 to xn, and I divide it by relations that they all commute. And this is a polynomial algebra, okay? I can do the same here. I'm giving you two sets of generators, in general, infinite sets. So I'm writing all possible words using these letters. And it's completely free to begin with. It's completely free. I can just multiply them and it's a word, like in a free group, You just write words with using your alphabet. So this is my alphabet. I have two sets of letters, capital letters and lowercase letters. And I'm writing all possible words using these letters, all possible finite words. But in a sister algebra, I can also take limits because I can define norms and I can take limits of these finite words and sums and so on. But then I define it by the relations. Sure. Sure, but this is something which comes next. This is something which comes next. You don't need it to understand the definition. That's representation theory. Okay, and what we are talking about is fundamental for proving that your favorite sister algebra, which you love and you want to study, can be represented as a graph sister algebra. These are very difficult theorems. Because what you do, you have some representation theory of your, for instance, take SUQ2 of Voronovich. This is a very famous sister algebra. Voronovich wrote faithful representation and so on and so forth. Yeah? And then this is where the art part comes in, hard and art. Yeah? You have to somehow feel that sister algebra, think of what it might be, write down your conjecture, you write your graph, you have your graph sister algebra, you represent it on a Hilbert space, and then you see that you can unitarily conjugate it to representation. And here's your proof that this is isomorphic. Yeah? But this is not straightforward. I mean, it's not like you have some sister algebra given by generators and relations, and you have some polynomial maps, which, I don't know, takes your generator x and y into generator x plus 2y. No, these are non-algebraic relations. This is when you use really operators in a Hilbert space to make sense out of it. Of course, you can also do it directly in simple cases, but this is still non-algebraic. Now, examples. If you know quantum groups, then you know also Waxman-Soibelman quantum spheres. Voronovich defined all these special unitary quantum groups. It's his famous paper from Invenciones. And Waxman-Soibelman, what they did, they took some SUQ n plus 1 and divided it by the action of a compact quantum subgroup of SUQN. And as a result, they got some fixed point sister subalgebra, and that's the sister algebra of the quantum sphere. Yeah. So this is just a classical, if you want, we mimic the classical situation where you can view odd dimensional spheres as quotients of SUN plus 1s by SUNs. Okay, this is how these guys defined it. And it's also given by generators and relations. You have all your odd spheres defined in this way. And you have some complicated Q commutation relations where Q is a real number between 0 and 1, but not equal to 1. And this is very, very important example in compact quantum group theory, okay, and non-commutative topology. But now imagine you want to understand the sister algebra, its topology. You want to understand how, I don't know, you can split it into smaller parts, how it is a boundary of a ball, how you can glue some things, how you can do some push-outs diagrams with this, okay? What are the generators of K? Here, K1 is interesting. When you go to, well, I don't assume that you know K-theory, but if you look at K-theory of the spheres, there are just two groups. K0 group, which is given by equivalence classes of vector bundles or projective modules. And then you have K1, which is based on the infinite unitary group of your algebra. And somehow when you go to spheres, for even spheres, K1 is 0. There's nothing interesting. And when you look at K0, you always have like the trivial bundle and very interesting non-trivial bundle. This is for even spheres. That's the so-called Bott generator, okay? If you look at the two sphere, this will be given by the Hopf-Line bundle. So people love it, Dirac monopole, physicists love it, and so on and so forth. Now if you go to odd spheres, like circle, free sphere, and so on and so forth, K0 is trivial in that sense that all bundles are equivalent to a trivial bundle. There's no interesting non-trivial bundle over an odd sphere, at least up to stable isomorphism. But when you go to K1, this is very interesting. For instance, over a circle, the generator of K1 is the unitary defining the sister algebra. But when you go to, for instance, to three sphere, you know, the three sphere is the topology behind SU2. SU2 has a fundamental representation. This is a unitary 2x2 matrix. Lo and behold, this is a generator of K1 of a three sphere. And it goes on and on and on. It's very fascinating. K1 is very fascinating for odd spheres. So once you prove that the famous Waxman-Soibelman sister algebra of odd spheres is isomorphic to the graph sister algebra for this graph. So you have a concrete graph. I told you how to assign to a graph sister algebra. So I have a graph sister algebra for this graph. And then using these tricks with representations, you can prove that in fact, these two sister algebras are isomorphic. So when I want to study things like K-theory, I might as well study the K-theory of this graph sister algebra. And this is much easier because I can now have a very nice and beautiful formula for the generator of K1, which is very non-trivial. I mean, it's just that K1 is Z, it has one generator. It doesn't mean that it's easy to determine the generator. Even classically, it's very hard to say what exactly is the generator of K1. Of course, you have some recipes and so on, but to have it very explicitly is not so easy. It's in fact much easier in the non-commutative case where you can read off by a very algebraic, formula you can read off a unitary element in a sister algebra, which you just cook up in a simple algebraic way from these projections and partial isometries. So this is an advantage. And in particular, you see, when you take your n equal to 1, so you have just a circle. There is no quantum circle. I mean, you might have quantum circle, but not in the spirit of quantum groups. So then you'll have only one vertex. So you have one vertex and one loop. And the graph sister algebra of such a simple graph is just continuous functions on a circle. Okay. When you take n equal to 2, so 2 times 2 minus 1 is 3. S3 cube. This is already non-trivial compact quantum space. This is the Voronovich SUQ2 sister algebra. So then you have only 2 vertices. You have one loop, you have another loop, and an arrow going from the first edge to another one. And graph sister algebra is exactly the sister algebra of Voronovich's quantum SU2. Okay. And then you go to higher dimensional Waxman-Sorbelman spheres. Now, one of the things which are going to be very useful for us in studying non-commutative topology is having an action. Just like you have the natural circle action on spheres, you just rephase complex generators. Well, here you can do the same. If you look at, just look at this definition of a graph sister algebra. If you say that an action of a circle is given in such a way that it leaves projection invariant, and it just multiplies a partial isometry assigned to an edge by one and the same e2i phi, then you see that these relations are satisfied. Yeah, because if I multiply s of y by e2i phi, and of course I multiply s x star by e2 minus i phi, so they will kill each other, and projections are invariant. Okay, the same works in other cases. So you see, now this, because I define this graph sister algebra as the universal sister algebra for these relations, okay, by definition, this action is continuous, so it's well defined. It survives the completion. Yeah, I define it on generators. I see that this definition preserves relations, and because I'm talking the universal sister algebra, then I have an action of U1 of a circle on a sister algebra. Okay, and this action always exists. It's so-called gauge action. You always have a circle action on a graph sister algebra. So what you have it in particular here, right? So what happens when you have 2n minus 1 dimensional sphere and divided by the diagonal action of a circle? We get projective spaces. And that's exactly how Waxman and Sorbelman introduced them. But before we do it, we also have balls. Somehow surprisingly, balls, which should be simpler than spheres, they came much later into the game. So this was done by the couple of Hong Szymański. Now, these guys really work together. It's not like Sir Swan. They actually married. Whoops. Yep. So they somehow answered the question of what are the balls that are bounded by these Waxman-Sorbelman spheres. So they defined them as they're even balls, of course, because if your boundary sphere is odd, then your ball must be even dimensional. And this is a graph. This is the whole Hong Szymański graph. And you can see how you get to the boundary sphere. Well, think in terms of classical topology. I have a ball, and I have its boundary sphere. I have an inclusion of the sphere as a boundary of a ball. And I look at the sister algebra of all continuous functions on the ball, right? Of course, I can restrict them to the boundary sphere. Okay? And this restriction is a quotient map. If you want, I divide by the ideal of all functions that are 0 on the boundary sphere. This is a compact closed subset in a compact Hausdorff space, so this condition makes perfect sense. I have a sister ideal of all functions vanishing in the boundary sphere. So when I divide all continuous functions on a ball by the ideal of all functions vanishing in the boundary sphere, what will I get? I get exactly functions in the boundary sphere, right? Because I look at functions on the ball, but I don't care if they differ inside the ball, as long as they are the same on the sphere, I identify them. So this is how I get exactly functions on the boundary sphere. So this is how this contravariant functor of Gelfand works. Okay, I have a subspace, I have a closed subspace in my Hajac space, and this gives me the map the other way around. I get the sister algebra on the subspace as the quotient of a sister algebra on the space. Okay, so the same works with graphs. I have my ball graph, Hong-Szymański ball graph, and I want to take a subgraph so that I have appropriate C-star projection from the C-star algebra of the ball onto the C-star algebra of the bounded sphere. So here what I have to remove, I just have to remove this vertex, and I have to remove all edges that end at this vertex. And then I'll get precisely the graph like in the previous slide, you see? And if you count the vertices, you will see that you will get from 2n ball into 2n minus 1 sphere. Yeah? So exactly the same recipe that you have in the usual topology works also for graphs. Okay, I can see the sphere graph as the subgraph of a ball, just as I can see the sphere as a subspace of a ball. Okay. But now I told you about this action. Well, by definition, the fixed point C-star subalgebra, so the C-star algebra of elements that are invariant under the action of a circle, well, this should be the algebra of functions on a quantum complex projective space. And this is how Waxman-Soberman defined it. And because this isomorphism between the original presentation of Waxman-Soberman quantum spheres and the graph C-star representation is actually equivariant, this is a non-trivial, non-algebraic isomorphism, but it is equivariant, having gauge action on one hand side and the obvious action on the Waxman-Soberman side. Okay, I immediately know that the fixed point subalgebra here will be isomorphic to the original defined Waxman-Soberman complex quantum projective space system algebra. Okay, and now here some interesting things happen. You see, now circles are gone, there are no loops. Okay. But all edges are all of a sudden countably infinite. So between, you see these arrows just as before, but now this is not just one arrow. These are countably infinitely many arrows going from one vertex to another in this combinatorics. And it turns out that the graph C-star algebra of this graph is exactly this Waxman-Soberman complex quantum projective space C-star algebra. And in particular, if you know Podle's quantum sphere, so this should be CP1. So you should take your number of vertices equal to 2 when you have CP1Q. So you'll have only V0 and V1, and you'll have only this one arrow here, but this is an arrow which actually stands for countably infinitely many arrows. So this is the graph C-star algebra of the famous standard Podle's quantum sphere. Okay. And if you want, it comes if you take Voronowitz quantum SU2. So this is given just by these two vertices and these two loops. Okay. You divide it by this circle action, which I just explained. Then you get a fixed point C-star subalgebra, and this will be the C-star algebra, which is given by this graph with two vertices and countably infinitely many edges from one vertex to another. And here's a certain pattern I would like you to notice. Yes, I have only one edge here, but I have countably infinitely many paths from this vertex to that one, because I can go by this arrow. I can wind around and go by this arrow. I can wind around a million times and go by this arrow. I can round around a million times here and go by this arrow and then wind around again. These are all paths from one vertex to another, countably infinitely many. Okay, so somehow this is what's going on. You have this circles turned into paths. But this is just a loose remark, so that you see that how these graphs are related. But this is a precise theorem. I'm not making it up. You can simply prove that the fixed point C-star subalgebra is isomorphic to this graph C-star algebra. Okay. Now, okay, have 20 minutes left, so there will be a sneak preview of some basic terminology we will use during the course. So first is just about paths. So what are paths in a graph? So a finite path in a graph E is a finite tuple of edges with the obvious property that the end of a preceding edge is the beginning of a following edge, right? And it's finite path because you have finitely many edges. Okay, so this is a path. Now, the beginning of a path Pn is by definition the beginning of its first edge. And the end of a path Pn is by definition the end of the last edge. This is also obvious, right? And very important, if the beginning of a path is equal to its end, we call it a loop. Unless it's just a vertex. I mean, but then this is, well, let me say, there are two things. So first, we can have infinite paths, and of course, it cannot be a loop. Yeah, you can have an infinite path, and when you just have countably many, you'll have a sequence of edges just with this property that the end of the preceding edge is the beginning of the following edge. And you can have an infinite path going in two directions. This is how you get compact operators, for instance, as a graph system algebra. But we also have, this is part of terminology. Of course, when you have a path, you can naturally define its length. Yes, this is the next definition. The length of a path is the size of a tuple. So Pn is the length and path, all right? And every edge is a path of length 1, obviously. But it's very important that vertices are considered as finite paths of length 0, okay? And of course, the length of infinite path is infinity. So you can have a loop as long as you have a finite path of length bigger than 0, with a property that the beginning of a path is equal to the end of a path. And here I have to also warn you that there's a lot of confusion of terminology. People call it cycles. For some people, a loop is just one edge with the same beginning and an end. This is crazy. I mean, the terminology is very confused. I decided on this because for me, a loop is a very generic thing. For me, a loop is just a map from a circle to a space. This is a loop. This is how we have it in algebraic topology. So if you have a loop in graph, it should be a finite path with the same beginning and an end. But don't expect that other people agree with this. Now, this stuff is completely standard, right? But now we needed to coin a new concept. I mean, it sounds very pompous, new concept. We needed this concept of a pointed path. This was needed for one of our theorems. So we say that the path is pointed if its final edge is not a loop. Okay. So if you go into an example, so every path ending here is pointed. Yeah. But if you have any path which ends, say, by winding around some non-zero amount of times by this loop here, then it's not pointed. Yeah. So a path go from here to there and wind around. That's not the pointed path. Okay. So this is what some basic definitions concerning paths. And now this is very important to have this set of all finite paths. And remember, all finite paths also includes vertices as paths of length 0, okay? And this space of finite paths might be infinite or might be finite, even if both E0 and E1 are finite, okay? It's obvious when E1 is infinite, then the space of finite paths is infinite because we have infinitely many paths of length 1, all right? But if you look, for instance, here, this is a finite graph. You have finitely many edges and finitely many vertices. But of course, the space of all finite paths is infinite because I can wind around the circle as many times as I please. Okay. And here I have a theorem. So this is a theorem which my daughter will prove for you next week. If E is a finite graph, then the space of all finite paths in this graph is finite if and only if there are no loops in E. One way is obvious, the other way you have to do some combinatorics. I mean, this is all very easy stuff, but this is already a theorem, okay? But this is still kid stuff, right? If you have 15, you can prove it. But this is something which came unexpectedly, and it appears to be a new theorem, which is kind of shocking. I mean, if it's true, if it's indeed a new theorem, because maybe somebody published it in German 65 years ago, I don't know, some journal of engineering, electrical engineering, okay? But when I spoke to people who eat graphs for breakfast, they said, well, it's true and it's new. And that theorem is already quite tough. Of course, depends on your experience. If you are professional graphers, it might be a piece of cake. But when we approached it with no technology, this was a hard work to prove it. And the original proof was 17 pages long. It took me several weeks to lecture the whole proof in Colorado. And I like this theorem very much because of the way you prove it. And it's also very conceptually understandable. I mean, you might ask such a question, and we ask such a question. So I take a graph which has n edges, but this n is at least 2. It has no loops because I want this space to be finite, okay, of finite paths. And I take a k, which is at least 1 and at most n, right? Then I'm asking a question. What is the maximal number possible of all paths of length k in a finite graph with no loops and n edges? That's the question, okay? But here, look, the situation is difficult because I'm looking at the space of all finite graphs with no loops. It's very hard to classify it. After all, I'm talking about all finite graphs with n edges, okay? So somehow the way we compute this number, the way we prove it, that if you have n edges in your graph, then there are at most that many paths of length k, and there is this bound is optimal because we can construct a graph which has precisely that many paths of length k. It requires operations on the set of all graphs with no loops and n edges, okay? And we do it by using Turing machines. We have some terminating algorithms. We take an arbitrary graph satisfying the properties. We throw it into a Turing machine. It's a terminating Turing machine, so it will put this graph into shape, spit it out. Then I take another Turing machine, throw it into another Turing machine. It will, again, adjust the graphs, goes on and on. The only thing which we have to prove at each step is what these algorithms do is that they never, ever decrease the amount of paths of length k. Okay, they increase in general, but they definitely do not increase. So this we are certain that whatever graph we start from, by applying these Turing machines, we will might produce, and typically we produce many more paths of length k, but we cannot go any lower. And then these two simultaneously operating, interchangeably operating Turing machines, they terminate at the graph at which we can immediately compute the number of paths of length k. And we know we cannot be any more because whatever graph you start from, by applying these Turing machines, you get by your terminating algorithms, you come to a graph in which is obvious how many paths of length k you have. Yeah, so this is how you optimize it. And well, this is how to imagine it. Well, if I look at this natural decomposition, so I take my number of edges, capital N, and I divide it by the number k, which is the length I'm interested in. So I see how many times k sits inside n, and then I have the rest, right? So this is just the obvious decomposition. I write capital N as nk plus r, where r is the rest of the division, okay? Just recall your last trip to Las Vegas, when you went into a casino to play cards, okay? Recall it. So now I have somebody dealing cards. So there are n cards, and capital N cards, and k players. So the cards are dealt in a natural way. So everybody gets at least lowercase n cards, but then this will be the rest left. And the guy dealing cards gives one card to our players. And then when you think instead of cards of edges, and you have the obvious combinatorics that basically you take edges which emit n plus 1 many, vertices which emit n plus 1 many edges, and there are r of them, and the remaining ones are there are k minus r of them, and then you just multiply to get all possible paths, and this is the optimal number. it's very hard for me to write. It will take a long time to switch into this whiteboard to write the formula, but this will be very carefully covered in the course. And this is a surprise theorem. We didn't expect it, we didn't intend it, we just proved it on the go. By the way, it was really fun. I was teaching actually mostly undergraduates in Colorado. So people much younger than you, no PhD students, right? 3 master students and everybody else was an undergraduate. And 20% of the whole course was based on research results that were obtained during the lecture course. It was the most amazing ratio I have ever seen. I mean, you lecture to undergraduate students and 20% of what you lecture is based on what you just proved. This is really fun. This is why graph histologies are exciting, because you can do many non-trivial things with very basic building blocks, okay? And this is one example. I don't know what it is good for. We surely don't need it for Leavitt path algebras. This was just like an exercise, yeah? You want to climb Mount Everest, but you see some beautiful rock on the side, so you climb it anyway. Okay, now, going back to textbooks.
I have a question for the
Go ahead.
previous slide. So what here do you mean by a loop? It is an edge with the same start and target?
I'm not, can you repeat your question?
So, okay, maybe you can hear me loudly.
I can hear you well, but I don't understand what you're saying.
Okay, so I have a question. What do you mean by a loop in the previous?
Loop, oh yes.
Sure.
Just as I said in my definition, a loop, path, and a finite path, and a finite non-zero path with the same beginning and an end. So I'm not, a vertex is not a loop. This is excluded, right? You see, I have this definition of a loop. Yeah. So this is a finite path with the same beginning and the same end. So it might be just an edge which begins and ends at the same spot, but you can also imagine that you go from one vertex to another, to another, to another, and after making 1 million steps, you come back to the beginning. This is also a loop.
Yeah, I understand. Because it's just that's a little bit different terminology than I'm used to.
Yeah. So I must, you see, but here it's look, oops. The one way. This is very simple to understand. Obviously, whenever you have any loop in your graph, your space of finite paths will be infinite. Because when you have a loop, you can wind around the loop as many times as you want. So you can have paths as long as you want, okay? But you have no loops and you have n edges, when it's obvious that the longest path you can have is of length n. There's no other way. If you have no loop, then the longest path you can have is of length n. Right? And of course, you have only one path of length n. So if you put k equal to capital N, this number p and n will be just 1. This will be a very stupid graph with just will be a path of n edges one after another. Okay, but it's getting very difficult. Well, let me mention it. But as long as you consider long paths that are longer than n half, then actually you can do it very easily. The trouble is when your paths are short, when k is less than n half, then the combinatorics gets crazy, and this is when we have to use Turing machines. I hope I answered your question. Now we do. Sure. Yes. Sure. Actually, this is a very smart remark. I really like it. You're right. For the first theorem, you must exclude loops. Otherwise, I mean, this is the whole point. You prove this is an equivalence condition. But you're right. If you would try to count all paths of length k, right? But all the loops in your graph would be of length bigger than k, then still the space of all paths of length k would be finite. This is a very good point. Bravo. I didn't think about it. This is a very, very good point. So you see how easy it is to start research here? You have already a new question. Try to prove a theorem about your question. And I guarantee it will be new. Okay, now back to textbook stuff. It's written all over the place. Graffiti on the walls. What is hereditary subset and what is a saturated subset? So the concept of hereditarity is something very important in order to define a subgraph. So the definition is very simple. A subset H in E0 is called hereditary if any edge that starts in the subset also ends there. So you do not allow a situation in which you have an edge which starts in H but ends outside of H. That's not allowed. Okay. If your set satisfies this, then it is hereditary. An example. Here, the set, the one element set consisting of W is hereditary. Well, because W is a sink, it emits no edges. So this condition is trivially satisfied. But the one element set consisting of V is not hereditary because V emits an edge which doesn't end in E, in W. It ends in W and W is not V. So this one element set consisting of V is not hereditary and the one element set consisting of W is hereditary. And this is very important if you want to define a subgraph. So I take a graph. So what do you think is a subgraph? Well, of course, your set of vertices in F must be the subset of the set of vertices in E, likewise with the edges. And then, of course, you have to demand that if you restrict domains and codomains of the source and target maps in E, then it will give you, by definition, the source and target maps in F. This is the most obvious definition of a subgraph you can come up with, okay? And lo and behold, you immediately have a proposition. Have a proposition that says that if E is a graph and H is a subset in the set of vertices, then if you define the new graph in the following way, that the set of edges in F is just the set of, not edges, sorry, vertices. The set of vertices in F is just the set of vertices in E, but without vertices which belong to H. So you just take the set difference. And then likewise, you remove all edges that end at vertices which are in H, okay? This will give you F0 and F1. You have two subsets, okay? Then you can prove that these formulas for the source and the target restrict to domains and codomains if and only if H is hereditary. So the hereditarity of the set is a recipe of how you can remove vertices so that you get a subgraph. If you do it in a stupid way, it will not be a subgraph. So if you, for instance, if you go back to this Hong-Szymanski ball, yes, this is a hereditary set. If I remove this vertex and I remove all edges that come here, I get a graph. It is a subgraph, okay? And by the way, you have an immediate exercise proof that it's equivalent definition if instead of an edge, I put in here finite path. One way it's obvious because an edge is a finite path, but the other way around, you have to argue. Yeah, this is like an immediate exercise you can do in your mind. Okay, whoops, my goodness, I should be, oh no. I should end in a minute and I'm 10 slides away. Okay, how should I do it? Let me do this one more slide. Yes, let me do this one more slide and I will pick it up in my, I miscalculated. And I'll pick it up in a week. Okay, so that we remember, we do 20 slides out of 30. Okay, this is, but actually, I will not be able to do it in 1 minute, and this doesn't make sense if I break it. Okay, so then we are going to define what saturated subset means, and then we are going to define what admissible graphs mean, and then we can get into some results. But let me do it in a week, because the time is up as of now. So let's make a 15-minute break. We'll switch from the slide presentation to the Zoom mode in which I will be able to see you on slides. So 3 students are here in the room and myself, so 4 of us in the room. And now, as I was warning you, I'd like you guys to introduce yourself just very quickly, like, 5 minutes each, so that I know your background. I know some of you, but not all of you. And it will be very helpful for me to know your strong points, your weak points. And I think it's fun to know each other. I know that it sounds like some weird therapy group now. but with say 16 people, I think it makes sense, especially 7 being PhD students. It makes perfect sense that you guys tell me what you work on, and I will try to see if there are any connections, and I'll try to guess what your flavors are, which you like. Okay, so let's call it a day with a lecture. Let's have a 15-minute break, and we'll resume at 2:15. Okay, now I stop here. Wow, talking through a mask for almost 2 hours is